All right, we're going to try it this way for once. There. Lucky chapter 13. Let me start off here by saying I miss you guys. I really look forward to this part in the year where we can start Lucky chapter 13. Okay, I'm being facetious. To see the look on your faces, some of you just scared because I'm going to use the word calculus so many times during this chapter. And then there's some of you who are going to, well, as you're watching this, you're going to be sitting there at home saying, I got this. What's the big deal? All right. This is what chapter 13 is. We're going to start with the idea of limits. A limit is there eventually. As the values of x get closer and closer to a certain value, in a particular function, the values of that function get closer and closer to a limit. Okay. So you need to know our lovely little notation here. So this is the limit as x approaches a of the function f of x is equal to L. They weren't very creative there. L stands for limit. So again, that's how you read that. The values of f of x get closer and closer to a specific value L as x gets closer and closer to a specific number a. Now the key thing here is it can't be exactly equal to a in most cases. Yeah, we'll just zoom in and out, in and out. The alternative notation they show you, and then you pretty much never ever see it again. X is not equal to a is in the definition of a limit. We never consider that x is exactly equal to a. It gets closer and closer and closer. So in these cases, if it's a continuous function, now again, notice here how for part B, there's a hole in the graph. I'll zoom in on that for a minute. For part A, it's nice and smooth, and there's no gaps, and there's nothing funky about that at all. It's nice and smooth. So as x approaches A, okay, so again, our lovely x value here, coming from this way, as x gets closer and closer to A, if we follow the graph, the value of the function gets closer and closer to the value that we say is L. Now, we put a hole in the graph. A discontinuity. We take this value out for whatever reason. It's defined as being down here. We're never ever going to never, sorry. We're usually not going to just substitute, okay? So we might have the false impression if we do substitute as x approaches a, that it's this value here that's the limit, and that's not the case. The limit is still this value up here. And even when there's a completely undefined value, there's a big hole in the graph, we will still say that the limit as x approaches a is equal to L. Now we could go through and estimate the limit there. I don't know where to put that. By making a lovely table of values. Okay, if you want to use your calculator for this and type that in as a function, remember you're going to have to mess around with the table settings so that you could change it to the finer and finer degrees of precision that we're going to need here in a moment. Now here's a good moment to stop and say, don't just substitute, okay? The limit as x approaches 1 of this function, if we substitute 1 in place of x, 1 squared is 1, 1 minus 1 is 0, we get 0 over 0. That's undefined. Oh, crazy things happen when you divide by 0, so let's not do that. But if we're looking for the limit as x approaches 1, we're going to put in values that are less than 1, but get closer and closer and closer from the one side. We're going to put in values that are greater than 1, but again, get smaller and smaller, closer and closer to 1 from both sides, okay? So for the values where x is less than 1, if we put in 1/2, okay, 1/2 minus 1 over 1/2 squared minus 1 will give us 2/3. We put in 0.9, 0.526316. We put in 0.99. Okay, again, these are values that are less than 1, but we're getting closer and closer. 0.502513. We put in 0.999, 0.500250, 0.9999, 0.50025. Well, that's interesting. It went from 0.6 repeating, 526, 502, 5002, 50002. Is there a limit? Okay, we go on the other side of it and pick things. I think that's a typo there. That should say greater than 1. So 1.5. Put that into our lovely function here. 1.5 minus 1 over 1.5 squared minus 1 will give us 2/5 or 0.4. We put in 1.1. Again, it's still bigger than 1. Terrible typo there. But we're getting closer and closer. We're backing it up. We're getting closer to 1. 1.1 will give us 0.476190, 1.01, 0.497512, 1.001, 0.499750, 1.0001, 0.49975. And looking at these, as we're coming from the left, as we're coming from the right, those values, as they get closer and closer and closer to 1, it looks like they're converging at the value of 1/2. So this is, again, one of the ways that you're going to be asked to do things here is to do this numerically, come up with a table of values, and approximate what that limit is based on what you see from your calculations. Or we could, again, graph, zoom, trace, but then zooming in, getting closer and closer, change the window settings, okay? Again, we talked about this before. This is one of those where there's a hole in the graph that you can't substitute one that's an undefined value. So they're showing here the x going from 0 to 2, the y going from 0 to 1. As we trace this from the left, as we trace it from the right, it seems to be converging at that value there. Basically, the y coordinate, the f of x value is 1/2. And they're showing here that they zoomed in a little bit, not a whole lot, from 0.4 to 1.1. Or, no, I take that back. This is messed up. This is the y from 0.4 to 0.6. And it's the x that went from 0.9 to 1.1. So they're zooming in closer and closer, and it doesn't matter. You come from the left, you come from the right. It looks like it's headed towards 1/2. Yeah, just to mess with you. Not every function is going to have a limit for every value, okay? And they pick this somewhat historical example here. engineer Oliver Heaviside can be used to describe the electrical current at a switch. Okay, so if the switch is turned off, the electrical current is 0. Flip the switch, complete the circuit, the electricity goes through at 100%. There's a jump in the graph. Okay, so if you remember the phrase, this is called a piecewise function. So if, again, they're using h of t rather than f of x, because again, it's the Heaviside function, and it's a function of time. So time 0 is when the switch is flipped. Okay, so before the switch is flipped, the amount of electricity is 0. Once the switch gets flipped, again, greater than or equal to, then it's 100% of the electricity going through there. Okay, but for the graph here, if we're looking for the limit as t approaches 0, well, if we're coming here from the left, approaching from the 0, it looks like the limit is 0. But if we say as x approaches 0 from the right, we go down and we get closer and closer, that looks like the limit is equal to 1. If those two from the left and from the right are not the same number, we say this limit does not exist. And yes, you'll be pleased. That's a lovely, useful TLA. Does not exist. And again, that's completely acceptable as far as I'm concerned, but that is your answer. Our symbols here, see, we're looking at, okay, as x approaches a value from the left, as x approaches from the right. All right, our symbols here, careful. This is the limit as h of t as t approaches 0 from the left. Okay. This is the notation that we use, the limit of h of t as t approaches 0 from the right. Okay, so from the right, we're going to see that little positive symbol. From the left, we're going to see the little negative symbol. So again, that's our definition of a one-sided limit. One-sided or the right-handed limit or the left-handed limit, those are fairly synonymous. Now here's another way of defining things. Once you get the hang of what's it look like from the left, what's it look like approaching that value from the right. Remember these biconditionals from geometry class? If and only if our left-handed limit is a value and the right-handed limit is the same value, then we say the limit of the function as x approaches a is equal to L. If the left-handed and right-hand limits are different, DNE does not exist. So here's a funky looking little monster here. So they want you to, let's go through and practice here. All right, so this is the function g of x. We're looking for, in part A, the limit as x approaches 2 from the left. So that means we'll trace our function here. We're looking at headed towards positive 2. So we're coming from this direction. We're going this way. We're following the graph. It looks like it's increasing. And as we get closer and closer, that the value here is, it's getting closer and closer to 3. Now, if we follow the same thing here, the limit of g of x as x approaches 2 from the right, that means we're going in this direction, we're going this way, and as x approaches 2 from the right, it looks like this limit is 1. So the limit of g of x as x approaches 2 does not exist because these two values are not the same. So now the limit of g of x as x approaches 5 from the left. All right, so let me get rid of these. So here's our value for 5. And if we're following this from the left, it gets bigger and bigger, and it looks like it's getting closer and closer to the value of positive 2. As we look at this function here, as x approaches 5 from the right, so we're heading in this direction, it's getting a little bit bigger, and it looks like it's also headed to 2. So this limit does exist, and it's 2. Okay, I think it's a great way of showing the left side limit, the right side limit. If they are the same, the limit does exist, and it's that value. If the left-handed and right-handed limits are not the same, we say the limit of the function at that value does not exist. And then they just explained everything that I did. And that's pretty much it. So get used to the notation, get used to the terminology here, and we'll see how that works.